So that was a lot easier using Keras, wasn't it? Now, the MNIST dataset is just one type of problem that you might solve with a neural network. It's what we call multi-class classification. Multi-class because the classifications we were fitting into ranged from the numbers 0 through 9. So in this case, we had 10 different possible classification values, and that makes this a multi-class classification problem. Now, based on Keras's documentation and examples, they have general advice on how to handle different types of problems. So here's an example of how they suggest setting up a multi-class classification issue in general. So you can see here that we have two hidden layers here. We have an input dimension of however many features you have coming into the system. In this example, there's 20, but depending on the nature of your problem, there may be more. It's setting up two ReLU activation function layers, each with 64 neurons each. And again, that's something that you would want to tune depending on the complexity of what you're trying to achieve. It's sticking in a dropout layer to discard half of the neurons on each training step. Again, that's to prevent overfitting. And then at the end, it's using a softmax activation to one of, in this example, 10 different output values. Okay, so this is how they go about solving the MNIST problem within their own documentation. They then use an SGD optimizer and a categorical cross-entropy loss function. So again, you can just refer to the Keras documentation for some general starting points on where to begin from, at least when you're tackling a specific kind of problem. Again, the actual numbers of neurons, the number of layers, the number of inputs and outputs will obviously vary depending on the problem you're trying to solve. But this is the general guidance they give you on what the right loss function is to start with, what the right optimizer to start with might be. Another type of classification problem is binary classification. Maybe you're trying to decide if images are pictures of males or females. Maybe you're trying to decide if someone's political party is Democrat or Republican. If you have an either-or sort of problem, then that's what we call a binary classification problem. And you can see here their recommendation here is to use a sigmoid activation function at the end instead of softmax, because you don't really need the complexity of softmax if you're just trying to go between 0 and 1. So sigmoid is the activation function of choice in the case of binary classification. They're also recommending the RMS prop optimizer. And the loss function in this case will be binary cross-entropy in particular. So a few things that are special about doing binary classification as opposed to multi-class. Finally, I want to talk a little bit more about using Keras with scikit-learn. It does make it a lot easier to do things like cross-validation, and here's a little snippet of code of how that might look. So here's a little function that creates a model that can be used with scikit-learn. Basically, we have a create model function here that creates our actual neural network. So we're using a sequential model, putting in a dense layer with 4 inputs and 6 neurons in that layer. That feeds to another hidden layer of 4 neurons. And finally, it's going to a binary classifier at the end with a sigmoid activation function. So a little example of setting up a little binary classification neural network. We can then set up an estimator using the Keras classifier function there. And that allows us to get back an estimator that's compatible with scikit-learn. So you can see at the end there, we're actually passing that estimator into scikit-learn's cross-val score function. And that will allow scikit-learn to run your neural network just like it were any other machine learning model built into scikit-learn. So that means cross-val score can automatically train your model and then evaluate its results using k-fold cross-validation and give you a very meaningful result for how accurate it is and its ability to correctly predict the classifications for data it's never seen before. So with those snippets under our belt, let's try out a more interesting example. Let's finally move beyond the MNIST sample. What we're going to do is try to predict the political parties of congressmen just based on their votes in Congress using the Keras library. So let's try this out. So let's play some more with Keras. Open up the politicsexercise.ipynb file in your class materials here. And that should be packaged along with these House Votes data files that we're going to be playing around with here. So go ahead and double click that. And up it should come in your browser. All right, and we should see something like this. Now this is actually going to be an example that I'm going to give to you to try out yourself as an exercise. So I'm going to help you load up this data and clean it up. But after that, I'm going to leave it up to you to actually implement a neural network with Keras to classify these things. So again, to back up, what we're going to do is load up some data about a bunch of congressional votes that various politicians made. And we're going to try to see if we can predict if a politician is Republican or Democrat just based on how they voted on 17 different issues. And this is older data. It's from 1984, so you definitely need to be of a certain age, shall we say, to remember what these issues were. And if you're from outside of the United States, just to give you a brief primer in U.S. politics, basically there are two main political parties in the United States, the Republicans, which tend to be more conservative, and the Democrats, which tend to be more progressive. And obviously those have changed over the years, but that's the current deal. So let's load up our sample data. I'm going to use the pandas library that's part of our scientific Python environment here to actually load up these CSV files, or just comma-separated value data files, and massage that data, clean it up a little bit, and get it into a form that Keras can accept. So we'll start by importing the pandas library. We'll call it PD for short. I've built up this array of column names because it's not actually part of the CSV file, so I need to provide that by hand. So the columns of the input data are going to be the political party, Republican or Democrat, and then a list of different votes that they voted on. So for example, we can see whether each politician voted yay or nay on religious groups in schools. I'm not really sure what the details of that particular bill were, but by reading these, you can probably guess the direction that the different parties would probably vote toward. So we'll go ahead and read that CSV file using pandas read CSV function. We will say that any missing values will be populated with a question mark, and we'll pass in a names array of the feature names so we know what to call the columns. Then we'll just display the resulting data frame using the head command. So go ahead and hit Shift Enter to get that up. And we should see something like this. It's just the first 5 entries. So for the first 5 politicians at the head of our data, we can see how each person's party is in the label that we've assigned to that person, the known label that we're going to try to predict, and their votes on each issue. Now we can also use the describe function on the resulting data frame to get a high-level overview of the nature of the data. For example, you can see there's a lot of missing data. For example, even though that there's 435 people that have a party associated with them, only 387 of them actually had a vote on the water project cost sharing bill, for example. So we have to deal with missing data here somehow. And the easiest thing to do is to just throw away rows that have missing data. Now, in the real world, you'd want to make sure that you're not introducing some sort of unintentional bias by doing that. You know, maybe there is more of a tendency for Republicans to not vote than Democrats, or vice versa. If that were the case, then you might be biasing your analysis by throwing out politicians that didn't vote on every actual issue here. But let's assume that there is no such bias, and we can just go ahead and drop those missing values. That's what this little line here does. It says drop NA in place equals true. That just means that we're going to drop any rows that are missing data from our voting data frame, and then we'll describe it again. And we should see that every column has the same count because there is no missing data at this point. So we've winnowed things down to 232 politicians here. Not ideal, but hey, that's what we have to work with. Next thing we need to do is actually massage this data into a form that Keras can consume. So Keras does not deal with y's and n's, it deals with numbers. So let's replace all the y's and n's with ones and zeros using this line here. Pandas has a handy-dandy replace function on data frames you can use to do that. And similarly, we'll replace the strings Democrat and Republican also with the numbers 1 and 0. So this is turning this into a binary classification problem. If we classify someone as belonging to label 1, that will indicate they're a Democrat, and label 0 will indicate that they're a Republican. So let's go ahead and run that to clean up that data. And we should see now, if we run ahead on that data frame again, everything has been converted to numerical data between 0 and 1, which is exactly what we want for the input to a neural network. All right, finally, let's extract this data into NumPy arrays that we can actually feed to Keras. So to do that, we're just going to call .values on the columns that we care about. We're going to extract all of the feature columns into the features array and all of the actual labels, the actual parties, into an all classes array. So let's go ahead and hit enter to get that in. And at this point, I'm going to turn it over to you for now. The code snippets you need were actually covered in the slides just prior to coming out to this notebook here, so just refer back to that, and that should give you the stuff you need to work off of and actually give things a go here. So I want you to try it yourself. Now, my answer is below here, no peeking. I put a little image there to try to stop you from scrolling further than you should. But if you want to hit pause here, we can come back later and you can compare your results to mine. Okay, so at this point, I want you to pause this video and give it a go yourself. And when you think you've got something up and running, or if you just want to skip ahead and see how I did it, hit play again and I'll show you right now. All right, I hope you did your homework here. Let's go ahead and take a look at my implementation here. Again, it's pretty much straight up taken from the slides that I showed you earlier. All we're going to do is import the stuff we need from Keras here. We're using dense, dropout, and sequential. And we're also going to use cross-val score to actually evaluate our model and actually illustrate integrating Keras with scikit-learn like we talked about as well. So when we're integrating with scikit-learn, we need to create a function that creates our model so we can pass that into cross-val score ultimately. We're going to create a sequential model, and we're just going to follow the pattern that we showed earlier of doing a binary classification problem.
So in this case, we have 16 different issues that people voted on.
We are going to use a ReLU activation function with a layer of 32 neurons. And a pretty common pattern is to start with a large number of neurons in one layer and winnow things down as you get to higher layers. So we're going to distill those 32 neurons down to another hidden layer of 16 neurons. And I'm using the term units in this particular example here. A little bit of an aside. More and more researchers are using the term unit instead of neuron. And you're seeing that in some of the APIs and libraries that are coming out. Reason being is that we're starting to diverge a little bit between artificial neural networks and how they work and how the human brain actually works. In some cases, we're actually improving on biology. So some researchers are taking issue with actually calling these artificial neurons because we're kind of moving beyond neurons and they're kind of becoming their own thing at this point. Finally, we'll have one last layer with a single output neuron for our binary classification with a sigmoid activation function to choose between 0 and 1. And we will use the binary cross entropy loss function,
the atom optimizer, and kick it off.
At that point, we can set up a Keras classifier to actually execute that, and we will create an estimator object from that we can then pass into scikit-learn's cross-val score to actually perform k-fold cross-validation automatically, and we will display the mean result when we're done. So Shift-Enter, and let's see how long this takes. Mind you, in 1984, politicians were not as polarized as they are today, so it might be a little bit harder than it would be today to actually predict someone's parties just based on their votes. It would be very interesting to see if that's the case using more modern data. Hey, we're done already. 93.9% accuracy, and that's without even trying too hard. So, we didn't really spend any time tuning the topology of this network at all. Maybe you could do a better job. If you did get a significantly better results, post that in the course here. I'm sure other students would like to hear about what you did. So there you have it, using Keras for a more interesting example, predicting people's political parties using a neural network, and also integrating it with scikit-learn to make life even easier. That's the magic of Keras for you.